In this lesson, we're going to discuss a specific type of infinite series called a power series. This pretty common series that we're going to see throughout the rest of the course is really important because we're going to use these series to model functions and differential equations and so on. There's lots of applications for this. We're going to look at this most basic thing called the power series. We'll say a power series is a series of the form in sigma notation. It's an infinite series of the following form, where there's a coefficient. I'm going to call it a coefficient sub k, so there'll be the 0th, 1st, 2nd, and then this coefficient sequence is multiplied to x to ever increasing powers. So note, if I write out what this looks like, this is really an infinite polynomial. It's got a constant term, and then it's got a first order coefficient, and then it's got another coefficient times x squared plus the third coefficient times x cubed, and keep going. So it's a polynomial that has ever increasing, integer increasing values of x, and then in front of each of those x's is a sequence of numbers. That's what the a subnumbers are. More generally, we would say that this power series that I initially wrote would be a power series centered at 0. We could center or shift our power series left and right in the following way, and we'll see this often. So there's still a sequence of coefficients, but now we could do x and shift it some amount where c is a real coefficient, is a real number, and it's called the center of the series. C is the center. Or we'll say this is a power series. This is a power series centered at x equals c. Most often for this class, they'll be centered at 0. But we'll often see maybe they'll shifted left and right in some way, shape, or form. But we'll worry about that later. These are infinite series, and we've studied up to this point when infinite series, interesting things about them are when they converge and when they diverge, meaning do they kind of center in, or do they hone in on a single number, or do they blow up to infinity or minus infinity, or behave badly in some other way. We had 2 tests for convergence that will tell us more about that, the root and the ratio test. In particular, the ratio test is going to be what we're going to use the most here, at least for this class. So we can use the ratio test to answer this question. For what values of x does this following power series converge? What are some x's I can plug into this, and then add up all the terms, and then see if I get a single real number, or do I get some crazy infinity nonsense? So we call the ratio test. Says that I should find the limit as n tends to infinity of each coefficient, or each term in the series divided by the previous term. Or in this case, the terms in this series are a to the n, so I think I want the next term divided by the nth term. And the ratio test says that when this limit, where then the n plus first term divided by the nth term, as long as this is less than 1, this converges. Recall, Also, when it equals 1, we have there's no conclusion. And when it's greater than 1, it diverges. So we'd like to choose what x's can we choose to plug in here so that this limit is always less than 1. Well, we can evaluate this limit. This limit is really x to the n plus 1 divided by x to the n. It's just x. And since I've divided out all of the indices, there's nothing left here. This limit at n approaches infinity of x is just the absolute value of x. So this converges when this is less than 1. So whenever the absolute value of x is less than 1, or better yet, how about when this means that x is somewhere between minus 1, this converges. What this means is I can choose any x inside this open interval, and I'm guaranteed that I'll get a convergent series, which means that the power of this is that this type of series is really what you think of as a function. I could think of this power series of x to the n as n equals 0 to infinity. This is really I could think of as a function, because I could plug in x's and then I could get real numbers out as long as the x's I choose are in this interval convergence. So this is really, we can think of this interval convergence as like the domain of this function. And as long as I choose x's in this domain, this power series will give me a bona fide real number, and life is good. And if I choose something outside the domain, well, this function really doesn't make sense. It just is infinity of some weird nature. So what we're going to do, and what we're going to focus our time on, is trying to understand what, for given a power series, what x's will make this power series converge, and therefore what x's make sense for this power series to describe a function. And eventually what we're going to hope to do is stumble across some ways to use these power series to represent functions we actually already know about, and try to use those to study those functions in ways we haven't before. Before we look at some more examples of this, I'd like to think about what this conclusion of that said, which is consider we have some maybe more general power series with some coefficients. And we suppose that this power series is absolutely convergent, meaning that we know that this converges for the absolute when x is the absolute value of b. We talked about absolute convergence in previous lessons. So what does this say? What more does this say about our series? If we know one value where this converges, say if I'm thinking of like the number line, and I have some value of b that I know this converges at. I know that this converges when absolutely when x is b, meaning I could put absolute value around this whole thing and it definitely converges. I know that this converges here. And it converges absolutely, so it converges at minus b. The idea is, well, are there any other values that this function would have to converge at? It turns out if you choose an x that lives somewhere between 0 and this number we know it absolutely converges at, say maybe x lives like here, then does this function converge at x? It turns out you can show that it does, and this is one explanation for why it would. It turns out that by choosing an x that's somewhere smaller than b but greater than 0, or in the interval between minus b and b, that it's not that hard to show that by the comparison test that the same series also converges. The trick is I take this general series and I multiply by, I think of a general term as the same term but multiplied by the endpoint b to the n divided by itself. Then with a little bit of algebra rearranging, I can show that this term is the same as a term when I plugged in b to the n times this term x divided by b. Well, x divided by b, since I chose an x specifically that x is smaller than b, that this term is less than 1. So if I take ever-growing powers of this, I'm going to be multiplying by smaller and smaller numbers, which means that this term, whatever this is, it's definitely smaller than this a sub n b to the n. Again, because x is smaller than b. But we supposed that that it is in fact absolutely convergent there, meaning we know it converges for x equals b. So if we compare this original series, if we compare the series we're investigating, a and x to the n, to this larger series, since the larger series converges, the smaller one must also converge by the comparison test. Meaning as long as I chose an x that's smaller than b to plug into my series, then we're good. What this lends to is that means I could choose any x in this interval, in this number line. Meaning if you can find one place where the series converges, you have an entire interval back to the center of where this series will converge. Or you have a larger domain than just the individual point. So what we're going to spend our time doing with these infinite series and these power series is to look at a power series and try to decide for what x's will it converge. And we're going to try to identify what's called the interval of convergence. And we can use the ratio test in order to do that. And I'd like to show you how. So suppose we have a power series. So we have some power series. This is some power series, and we're going to apply the ratio test to try to determine for how we can make this thing converge. So the ratio test says that the ratio test would look something like this. I want to find the limit, n heads to infinity, of the n plus first term. So this would be a n plus 1 x to the n plus 1 over a n x to the n. And the ratio test says that when this is less than 1, this converges. Okay, so let's simplify this. This is limit n heads to infinity of a n plus 1 over a n x n plus 1 over x n. We saw earlier that this is just the absolute value of x. So this is really just this limit times the absolute value of x. And this converges when this is less than 1. So what x's can you plug in? Well, x's we can plug in are x's such that when we evaluate this limit of this ratio, times x is less than 1, or maybe better yet, we'll try to simplify this a little bit. I'm going to give this limit a name. I'm going to call whatever the limit of the ratio of the coefficients is, I'm going to call this limit L. So this tells me, so that this ratio test tells me I'll have L, which is the limit of the coefficients, times the absolute value of x. And this should be less than 1. Or better yet, when the absolute value of x is less than 1 over L, this converges. I did this just for power series centered at 0, but you could, there's no reason why you couldn't, this exact line of reasoning would work if you centered this at some other value, say c. all we have is x minus c's in here. In any event, what this tells us is that if we can figure out what L is, or what the limit of the coefficients is, then we'll know how big this interval is. This 1 over L often has a name. The name we give this is called the radius of convergence. Because this 1 over L tells us how big the interval is. In my mind, I think there are 3 cases of what L could be. I think L could be 0, in which case the radius of convergence would be 1 over 0. Put that in quotations because this would mean it's infinity. Meaning the series converges. The radius converges is infinity. That means the series converges for all. No matter what x you choose, that this x minus c will always be smaller than infinity. Meaning any x you choose will always make this a convergent series. I think the other extreme case is that this limit could be infinity, in which case the radius of convergence would be like 1 over infinity, which is 0. This means that the series will only converge at whatever the center is. And then lastly, there's also, I think then the other condition would be that this limit is not 0, but also not infinity. So it's just some real number. And this tells me that the radius of convergence is just 1 over whatever this limit of terms is. Note that you could, alternatively, you don't need to figure out specifically what 1 over L is. You can just solve rearrange the ratio test so that the absolute value of the x term is less than some number. And whatever that number is will be the radius of convergence. So to find the interval convergence, the interval I'm going to solve this absolute value inequality, x minus the center is less than this radius of convergence. Solving absolute value inequality of this type of less than, this is the same as minus 1 over L is less than whatever x minus the center is less than positive 1 over L. Or add c to all sides, so you get c minus 1 over the minus the radius convergence is less than the x's I'm allowed to choose, which is less than c plus the radius of convergence. This interval would be what the series was guaranteed to converge at. You also, since the ratio test is inconclusive when the limit is equal to 1, that means it's going to be inconclusive when I plug in the endpoints. We can make it conclusive if I take the values of these endpoints and substitute them in for x into the original series and use one of our many other tests for convergence. And that will tell us whether or not the series converges at the endpoints, or whether I could put an or equal to under any of these. And that'll be a little more clear when we do a few examples.